Good evening, good morning, everyone. Welcome back to our Game Changer seminar series. My name is Mark Sargent. I'll be your host today. I'm the EC Science Program Manager, and it's my pleasure to welcome Oliver Hahn for today's talk. So Oliver is an expert in simulating the universe, and more specifically, the different structures which form really the scaffolding of the universe in the dark matter phase, and their interplay with the galaxies that form within these structures. So yeah, Ollie's talk today is called Structure Formation and the Cosmic Web. And for those of you who joined last week for the talk about early universe galaxies, and maybe even asked questions about the dark matter context, this, in that case, today follows on nicely from what we heard last week. So before we begin, let me introduce Ollie's pathway to these questions, his scientific pathway. So Ollie started out with a PhD at ETH Zurich. He then moved on to KIPAC at Stanford, so KIPAC being the Kavli Institute for Particle Astrophysics and Cosmology. After that three-year postdoc in California, Ollie returned to Switzerland, to the ETH, with a Ambizioni postdoctoral fellowship, and then as his first permanent position after that second postdoc, moved to OCA, the Observatory de la Côte d'Azur in southern France. Ollie was a ERC grant laureate during his period at OCA, and that enabled him to build a nice group working on these questions. And he then took this group with him for his latest position in 2020, when he joined the University of Vienna as a professor for data science in astrophysics and cosmology. So yes, Ollie, we're looking forward to your talk. For the audience, I'd just like to remind you, if you're joining for the first time today, how we go about posing questions. You can open your chat window if you have a question during the presentation. The question will be recorded there, and when Ollie has finished speaking, we will then go through those questions. We will also take questions directly from the audience after the talk is over. So if you want to ask a question in person, you can raise your hand at the end, and then we will alternate between in-person questions and questions taken from the chat. So yes, Ollie, I'm looking forward to your talk about filaments, voids, and everything else which the dark matter web entails, and I'm sure it will be everything but devoid of interest, in the spirit of making a pun. And yeah, the stage is all yours.
Thanks so much, Mark, for the very kind and nice introduction. Yes, so I'll try to take you a little bit to the largest scales that are still structured in the universe today, where it comes from, how it kind of connects with galaxy formation processes, where it comes theoretically from, and whether we can observe it, whether it leaves any imprint on observable things, and questions like this. So let's start. Whoop. Okay, here we are. So as we all probably, that you followed this seminar series, you've seen this picture before, which is a picture of the microwave sky taken by the Planck satellite. We of course see the Milky Way in the front, and as cosmologists, that's just one of many, many, many galaxies that we can observe. And so typically we like to remove that foreground, and what comes behind it is the microwave, the cosmic microwave background, which we believe is the baby picture that reflects all the perturbations in the early universe that have seeded all the structures that we see today. So galaxies, the first stars, galaxy clusters, and the like. We typically quantify, of course, this in terms of a fluctuation spectrum that connects these temperature fluctuations that one sees in the microwave sky to underlying fluctuations in the metric, or if you want, the density, more intuitively. And these tiny density perturbations then grow in the expanding universe under gravity to form today's universe. And so a very nice picture of the sort of corresponds in its full sky nature to the microwave sky is one taken by the TUMAS galaxy survey, which shows every dot that you see here corresponds to a galaxy. And what we see is as well that the dots are colored by the redshift. Redshift is a distance indicator, as you know. So things, points of a similar color corresponds to galaxies at a similar distance. And so what we see very clearly by eye, our eye is very trained to do that, is that these galaxies do not form what we call a Poisson set. They are very much structured. They form these filamentary regions. For example, here we see very clear filaments with node-like structures that are probably the most massive structures that have collapsed in the universe. So we get these kind of cellular structures that we see, and that is the cosmic web. This is another picture of an earlier survey, 2001, the 2-degree field galaxy redshift survey. That sort of is a different view of this, where here we see the projection onto the sky sphere. Here we see the Milky Way is located at the center, and we're looking out in radial distance. And so what we see is that the sampling of galaxies at a fixed luminosity limit goes down, but we very clearly see the same cellular structure. So how is all this connected? Well, at the linear level, it is the power spectrum that we saw before of these fluctuations in the temperature simply gets translated into a power spectrum at late times. And similarly to the curve that we had before, that shows the Planck measurements with a perfect, almost perfect fit from lambda CDM, we can repeat this with late structures. So Planck results are actually also on this, but so are later results. And so all in all, I'm not going to go too much into those details. All in all, we have a picture that sort of relates the early universe with the late universe that is held together in the lambda CDM standard model. And apart from several tensions that have emerged maybe over the last years more prominently, the general picture fits extremely well. And we are in the regime where sort of these deviations are at the properly physical, not so much at the astrophysical level anymore, but we're talking about percent level accuracy. So how do we model this? Typically, this relation between the early universe and the late universe is done with simulations. And so the latest, one of the biggest ones was actually run in Switzerland, which might maybe be nice to hear for the audience at EC. One is the Euclid flagship simulation that we see here that starts from sampling with particles, the distribution that we see from the cosmic microwave background, and then evolves this forward in time. And so what we see is we reproduce the same cellular structure and the same distribution of galaxies. And so by probing this cosmic web-like structure, we can then infer information about the structure formation model and the physics that's underlying our universe. And these cosmological simulations, as we call it, are the most robust or the most precise tool that we have to sort of make this link between the structures. The problem is a bit that we have a very high parameter space, high dimensional parameter space of cosmological parameters that we want to infer. And so one aspect of the whole game of making these predictions, making these links is to understand this better, to optimize this, to be more precise, to be more robust, and so on. So I'll also get into those aspects. So just as a general framework of what we're doing is that we're now in the era of precision cosmology. I'm sure many of the other people in the series have also talked about this. And so when we talk about the late universe, we're probing the entire history of the universe. So we're going from the epoch of the CMB all the way to the epoch of today's universe on the large scale. So what you see here is the same representation of the TUMAS survey that we've seen before, but in the exact same coloring scheme as the Planck. And so what you see immediately is that the structure is much, much more clustered. The density contrasts are much higher. This is a non-Gaussian field, a highly structured field. And this mapping in the end between the two contains the whole structure formation model, contains information about the cosmological parameters, contains information about the nature of dark matter, contains also information about astrophysics. And so this is what we do when we talk about precision cosmology of the large scale structure, is to understand this link and to infer information about the content of the universe, about the laws of gravity, and so on. In a first order model, however, we can sort of simplify our equations and leave out all of the astrophysics to get most of the phenomenology. So this is what we'll start with. So in that sense, on large enough scales, we can assume that this cosmic fluid of matter, of dark matter mostly, of galaxies and so on, can be described as a fully collisionless, pressure-free fluid. This is fully justified because we're talking about completely non-relativistic matter, and we restrict ourselves to large scales. This is the only equation, I think, that I'm presenting. I just wanted to give a flavor for how we simulate them or how we describe such systems. So what we model this is as cold matter, collisionless matter, which is described by a Boltzmann transport equation. So what we say is just the matter is distributed in some way in position space, momentum space, and then flows over time. And we start off with a homogeneous isotropic state in the beginning, and then these structures evolve over time. And so then the Boltzmann equation simply has a term that means if something has a velocity, it moves in space. And if something has a gradient in the potential, then it moves in momentum space, meaning it accelerates. And the whole distribution is then nonlinearly coupled to the Poisson equation. Okay, terrible system of equations. We can feed it into computers and solve it with particles by discretizing this equation. But we can also do a simpler approach, and this is what the Seldovich approximation does. This is basically one of the first theoretical hints that was found to point towards the emergence of the cosmic web. How can you imagine this? So if you solve these equations, you solve them along so-called characteristics with the particles methods, like an n-body method. What this means is you think of the initial state of the universe as perfectly homogeneous and isotropic, and then every fluid element moves. And this displacement between its initial position Q and its final position X defines then sort of a mathematical map between them. Now, what we have is we've initially the kind of metric perturbations in the early universe that cause these trajectories to be not all parallel to each other. And so what happens then is we think as time going downward is that we start with perturbations, and then at first order, all the particles move along straight lines. So if there were no perturbations, they would continue on straight lines, but because there are perturbations, they sort of are deflected, and at some point they cross. And so this process, actually, you can think of this as very similar to the formation of caustics at the bottom of a swimming pool that you probably, hopefully, have witnessed this summer. So we have light rays coming in parallel from the sun, being randomly deflected at the surface of the swimming pool. And what we see at the bottom of it is this random caustic pattern that comes from this diffraction at the surface. And what we immediately see as well is that we have the same sort of web-like structure that we also saw in this galaxy distribution before. And so if we translate the same thing into not having two-dimensional surface at the bottom and one-dimensional depth, which is the time dimension, but we do it in 3D, then we have basically our universe. So we can think of this as particle trajectories basically being a deformation of a piece of three-dimensional paper, and we're just folding it onto itself. We're distorting it, and we're folding it onto itself. And this is how the structure in the cosmic web forms. So this particular pattern that we get follows then directly from the mathematical properties of this map, because if one writes down the density, I don't really want to go too much into details, but the density follows from a second derivatives of this potential. And then all we can get is four distinct, one has, sorry, this is in 2D. I should have, I forgot to correct this. We get four distinct structures. We get void structures where sort of we have an expansion in 3 dimensions. We get filament structures where we have a compression in 2 and an expansion in 1. We get node-like structures where we collapse in 3, but we also get planar structures. We have sort of a convergence in 1 dimension. And this sort of pattern formation and how it emerges was actually already realized in the 1970s, which is one of the first computer simulations made using this approximation in 1977 in Russia by by collaborators of Zeldovich. What you see on the right is a little computer program that I wrote that does the exact same thing today in real time and looking a little bit better, but the picture is the same. So we have these regions that sort of have signature of expansion. Then we flip one axis to being collapsing. We get a planar structure. We flip one more. Then instead of a planar structure, we actually get a filamentary structure. And the node is something that collapses along all 3 dimensions. So for those who are mathematically inclined, in the end, there's a beautiful mathematical structure behind this, because all of this sort of phenomenology that appears is connected deeply to what's called mathematically Morse theory. So it's a characterization of the properties of this perturbation in terms of critical points. A critical point is, for example, a maximum. You sit on a maximum and you will just sit there. If you move slightly away from it, you will roll down, right? So now you can think of, if you're a maximum in 3D space, you can roll down in all dimensions. If you're a minimum, you will converge toward it. If you're a maximum, sort of a saddle point in 2, but not in the 3rd. So you get the picture. So we'll get exactly structures like these walls, filaments, nodes, and regions which are just expanding in all 3 directions. And so we can classify the perturbations based on such a Morse theory map and understand which regions will fold up in these different ways and give rise to these different structures, these different morphologies that we observe in the web. So once things move and fold, what happens then? In this picture of the Zeldovich approximation, it will just pass through it. So it will be a very transient phenomena, and it will just disperse again. This is, of course, not what happens. So what happens is what we see here. This is a little one-dimensional simulation of cold collisional fluid. So we have a velocity perturbation. That stuff moves here with a positive velocity to the right. Here we have a negative velocity. Things move to the left. The point is that it's a fluid, so it has a continuous structure to it. So if we run this forward, we have the moment of caustic formation when we have a vertical tangent here. And then afterwards, because this is position space, we'll have a sort of many particles moving at different velocities, moving here with negative and so on, here with a positive at the same location. We'll have a region which is outside where nothing has sort of what we say shell-crossed, and we have a region where it forms a bound structure. And so this is this folding process that's really happening in the large-scale structure. So we're sort of distorting things, and then as they start to overlap, we're sort of winding them up locally. We can do this in 1, 2, or 3 dimensions in a 3-dimensional universe. If we have a normal gas, then it will not be collisionless, but instead what will happen is that as soon as particles start coming together at the same location, they start scattering over each other, and we lose all of the information in here that we had about the initial conditions. That's sort of the coloring here. And we'll sort of go towards the formation of a shock and towards the formation of a high entropy state, where we get sort of a well-mixed particle structure. So while if you have a collisionless system, no entropy is produced, and instead we sort of retain all of the information. The problem is just that it all overlaps in some space. So if we cannot disentangle it from this information would be lost. So if we sort of now plot this in a different way, the spiral, it looks like this. So now instead of having it all evolve over time, as a movie, we plot the time here and we omit the velocity dimension. So what we see is this is space and this is time, if you want. Special time coordinate, never mind what exactly it is. So what we have is particles moving towards each other towards the overdense region. Then at some point, all of a sudden forming a Shocks-like structure, a caustic-like structure, and then forming a bound state of a virialized system, as we say, as astrophysicists. So this is a very important diagram, even though it looks maybe a little bit academic. Why? So we have here a perfectly homogeneous universe to start off. And the only thing we change is the velocity of the fluid elements in this space. And that causes, from something that has no density perturbation whatsoever, perfectly maximally symmetric, then causes all the perturbations later on. And in this early phase, the Zeldovich approximation before, everything is straight lines. And then afterwards, after the structure forms, of course, it cannot be, and we form this bound state. Why is this important? So the problem is, because of all these singularities, mathematically, it is a very hard problem to treat in a framework when we do not want to simulate it with many billions of particles on a computer. And so this moment of what we call shell crossing, the formation of the first bond structures in these equations is a mathematical subtlety that sort of has hampered most theories that have not resorted to simulations. And so this is a very much an ongoing aspect of research. Can we extend the mathematics to describe these systems in the context of this very simple evolution that is outside of them? And it's a very interesting problem that we're also interested in a lot. But if we run it with a computer, it's a perfectly simple problem. So now you can ask, of course, all in here, in some sense, if we only have access to position information about initial conditions, so everything that lived here is lost. But at the same time, sort of if we discard information, we go to a high entropy state in the sense that the only observable that we then have is the mass of the structure. And that's, of course, in the end, very critical cosmological observable, as well as everybody who does classical cosmology knows very well. So just to give you then a feeling going back to 3D rather than simple 1D, this is a movie made by Jens Stücke, because before we had two-dimensional movies. So now we're looking at this folding structure of the cosmic web in 3D. So what you see is a perfectly thin slice through this cosmic web, and we're just moving the slice without having any evolution in time, moving it along one of the axes. And so what you see is that it's really a very continuous structure of these sort of void-like regions, of these filamentary regions. Everything so persists over time is a planar region, right? Because otherwise it would be very transient as you move on one axis. And so the cosmic web, if you want, is a much more complicated structure, a much more intricate structure than the simple picture that we very often get from structure formation as just being galaxies that merge, and we have a merger tree that where we have individual objects that over time merge in the structure to form more and more massive structures where everything lives in halos, where everything is a galaxy. If we go to this cosmic web picture, then it's really a picture of things flowing and folding together. So if we have a merger, then it means that there is always associated structure that sort of coalesces as well. Do we care about this at the level of galaxy formation? Well, that's a question we'll actually get to in a moment. What's also interesting is because sorry, this is not running. Okay, here we go. So because we are not, do not have collisional systems, so as we had before, we do not lose this infall information. And so a little study that we did some time ago was to see if how anisotropic then this random motion inside of the collapsed structures is. And so what we found is that we can actually exactly recover these different web environments also at late times by just measuring how anisotropic sort of the random motions are in them. And so we just color here the motions by how anisotropic they are, sort of the codimension of these motions. And so we recover all these distinct web environments very, very clearly. So we have very isotropic things, which are the nodes, which are the galaxy clusters in large scales. We have very anisotropic things, which are these walls. And you clearly see them existing in these sort of three-dimensional movies, as well as these filaments. And of course, the void regions as well. Okay, sorry. I went ahead too fast. Good, so all nice and good. Do we care about this at the level of, can we actually observe it? So of course, there are many ways to observe it. The first one you've seen already. We've seen it in the galaxy distribution already. But of course, in these filaments, if we go to higher redshift earlier in the universe, we'll have a lot of gas that feeds galaxies. And so one aspect that's very interesting is to look, can we sort of recover this information? And so a beautiful example in this direction was an exercise that was done by people from the Clamato survey. So what the Clamato survey did, it takes many, many, many sightlines to quasars that are sort of in a very localized region on the sky. So we have a very dense packing of background quasars, so very high redshift black holes, if you want, that emit very brightly. And so as the light then from the background travels towards us, it will travel through the intergalactic medium. And as it travels to the intergalactic medium, it's redshifted, and every time it encounters a cloud, we get an absorption feature into the spectrum, and then it gets redshifted as it travels further. Then we get at the rest wavelength of a gas cloud again, an absorption feature. And so in the end, we get a spectrum that reflects the distribution along a single line of sight. And so having many of these lines of sights, now one can sort of do a tomographic reconstruction. So very similar to what you might have if you're unfortunate at a doctor's appointment, and reconstruct from a few of such sight lines the three-dimensional distribution. And so this is one attempt to sort of reconstruct in 3 dimensions this cosmic web structure. This will then give critical information, for example, to see what are the environments of high redshift galaxies, protoclusters that form sort of more massive objects, and so on and so on. Itself, it will also provide sort of a consistency test of structure formation at intermediate redshifts. This I already said. Well, what we started off, of course, we have detected, we know the cosmic web. This started my presentation, some is from the galaxy distribution. There's more we can do with the cosmic web. One thing is, one of the biggest mysteries, and I think this is one of the next upcoming talks, is the nature of dark matter. So as we know that about 80% of the matter in the universe should be in the form of dark matter, but we do not know what it is, we would like to probe different scenarios. And most of these scenarios of different dark matter kinds make very clear predictions about how the perturbation spectrum of these early universe perturbation is changed for different kinds of dark matter. And so what you see here is, for example, if we have a cold dark matter, the spectrum would continue to small scales, but then for different kinds of dark matter, this might be sort of smoothed out on some detectable scale. And so what happens if you smooth things out? Well, then you change basically the clumpiness of structures inside of the small scale cosmic web. And detecting sort of these filamentary versus clumpy structures, for example, through gravitational lensing, might provide a very sensitive way of probing this faint end of the halo mass distribution and thereby constrain the dark matter model that might explain the dark matter that we see in the universe. Another application of the cosmic web is, of course, that what I mentioned before from the Lyman alpha forest is that it contains gas, neutral gas, cold gas that feeds galaxies, especially at high redshift. And so what you see here is a result from a simulation where we did actually just plot the distribution of gas around the simulated high redshift galaxy. And so what you see in blue is the cold gas, and then this is even slightly colder gas that is accreting onto a galaxy. And so what you see is this is clearly embedded in such a pancake-like structure. And you see also these filaments that bring in the cold gas. And I think it's by now established that this makes high redshift galaxies, or during the dawn of galaxy formation, very different from the galaxies of today. They accrete a lot of gas. They're very gas dominated. They form a lot of stars. And again, this is how they connect, or were back then connected to the structure of the cosmic web. So this is what you would see in terms of the gas distribution, the gas entropy, if you were sitting in such a high redshift galaxy. And so you clearly see sort of the filaments coming in here, here, and here, and you see this pancake-like structure in which you're embedded. And you see it outlined by shocks, which are the outer part of these caustics where matter is just accreting onto these structures. So one question we might ask is then, are we expecting that sort of these differences in the large scale structures could influence galaxy evolution? Could they change if a galaxy is hosted in such a filament, if it sits at a node, or if it sits somewhere else? So this is a question that has been studied immensely in the last years. For various reasons, for understanding galaxy formation in itself. So for example, the picture here could be that we have a star-forming galaxy that sort of accretes, that has its own filaments, but then accretes into a more massive filament and loses thereby all its inflow of cold gas. And thereby gets sort of quenched by detaching from its inflow of cold gas. This is sort of still eluded this picture a little bit, the investigations with the simulations. It's a bit unclear whether this can really work to play a major role in galaxy evolution, but it is one possibility. Other processes that were observed in simulations that you see here, for example, is the stripping of Milky Way satellites in the filaments. So the idea is exactly something like this. We have a Milky Way satellite that sort of falls in early and then falls into the Milky Way and thereby loses a lot of its gas early on, thereby changing its properties from some of the others. We also know from simulations as well that even mergers between galaxies end once they sort of accrete onto these filaments. So this was an exercise that we also did many, many years ago by now. 2014, we found that actually the last major merger happens precisely when sort of you for the last time you accrete on a filament and not so much afterwards. So there have been many studies now trying to exactly disentangle and find such effects on galaxy evolution. This means that in some sense you want to detect and classify these different environments in the cosmic web and then probe does galaxy formation proceed differently if a galaxy of the same mass sits in different environments. And so very often then these studies proceed like this. We have a galaxy distribution, we infer some mass distribution from this, and then we classify it using some classifier into these different distinct environments. And we would think that everything that sits in a knot sort of dominates its environment, and things that sit in filaments might still do so. While if you're in a void, then you might have a very different history. And so this goes in one direction. Sort of a very interesting approach that's been taken by others is to sort of see this as an inference problem, where because if we sort of have the initial conditions, we can exactly predict how the cosmic web forms and how its dynamics is. And so this is a nice analysis done with a SDSS survey. So we have sort of a slice from the survey here, the galaxy distribution, and then a Bayesian inference framework is used in order to sort of look for the exact initial conditions that gave rise to this galaxy distribution. So that gives us then the initial conditions of exactly that patch of the universe around us, or at least the initial conditions that are consistent with all these observed structures, and then we can classify them. And so this worked extremely well in this example where you see that having this additional information about the initial conditions gives you a very clean separation in these different environments. Then you can ask questions like, does galaxy formation depend on environment? So this is an example in this direction. Where there was a claimed detection of a segregation of passive galaxies versus galaxies that form stars as a distance of where you are in the filament. So the idea is that if you're still outside, then you still have your gas, but then once you're sort of inside, you get disconnected and you lose that supply from gas. This was done with the Cosmos survey, and they did find a signal. The problem in these studies is always it's extremely hard to control for secondary variables like the mass. And we know that the halo mass, for example, in simulations is the determining factor. So this is still an ongoing question, how much this is driven by possibly halo mass, or how much it could be indeed a signature of the impact of a cosmic web environment. So the problem of any of these sort of correlations of galaxy structures with the cosmic web is, well, there are two aspects to it. There is the aspect, of course, for galaxy formation. If we want to have a whole picture of galaxy formation, we want to know if the environment of galaxies matter or whether it's all internal processes. But there's also the cosmological side to all of this, is if we want to use galaxies to probe the large-scale structure, then the galaxy should be better not too much influenced by the structures where they are. Otherwise, we might create sort of biases in our analysis. And so this is why these kind of effects are very important also from the cosmological side. This is just a sort of a similar analysis that was done more lately. This one I was part, there's another one by Shabab Alam, those were in 2018, where we just looked at if we split by environments, we do find a signal, but then if we split by environment and control for mass, in the simulation, we find a very similar signal. So at least for the low redshift population, it seems like it could all be explained simply by halo mass. But of course, we know also in the low redshift universe today, most galaxies are not forming stars much. And so it will be very, very interesting sort of to extend these kind of analyses to a more high redshift universe, where we know that galaxies are very, very much dominated by the accretion of fresh gas into them. Another example, maybe one of the most prominent of the influence of the cosmic web on galaxies, actually dates back to the 80s already by Bingley, who found that the galaxies that sit in the centers of very massive galaxy clusters, they tend to have preferential alignments. They do not tend to have a shape that is completely random, but they tend to be aligned with the distribution of galaxies around them in the galaxy clusters. So sort of, if we have a galaxy that's elongated in this direction, then most of the cluster galaxies seem to show a preferred ellipticity that's sort of aligned with the central galaxy. And so the reason for this is that the merger processes that form the cluster are, of course, correlated with the cosmic web. And so we have a preferential infall directions where satellites come in, and along also preferentially the last major merger might happen for these galaxies. And if, of course, a central cluster galaxy is aligned with the filaments, that means then that most likely there will be the central galaxy of another galaxy cluster will also be aligned with the same filament, because filaments are at first order simply straight lines. And so we get a very long range, large scale correlation between galaxy shapes. That is a curiosity, but it is also a big problem for gravitational lensing. So I don't know if you have another talk in this series about weak gravitational lensing. So I will just give a sort of a short introduction, never mind the equations for now. The idea is we have a foreground mass distribution and we have a hint and a background distribution of galaxies. In this picture, the background distribution is just a grid of spherical galaxies. Those galaxies are not perfectly spherical, nor can they come on a perfectly regular grid. But this grid is distorted because of the gravitational lensing effect. So when we get these big arcs or possibly even rings, we talk about the strong lensing regime. But if we go away from these sort of strong mass concentrations, we see that we still get some signal, we still get a distortion of the shapes. But in addition, by going to larger radii, we get many, many, many galaxies, right? Rather than a few that are lensed. And so the idea of weak lensing is to use the statistics of many, many, many of these more weakly distorted galaxies to infer the distribution of foreground mass. So now you might see immediately the problem. If the shape of a galaxy, of course, is not exactly a little disk, but it is, if we go away from it, it is already an ellipse, the image. And these ellipses are not randomly distributed, then what we'll get is the correlation between ellipticities that we see here. So we correlate two ellipticities, and then we get the correlation between the two lensing-induced distortions of the galaxy shapes, which is the signal we want to measure. But, of course, we get also the correlations between the intrinsic shape of the foreground galaxy and that of the lensed galaxy, as well as the reverse, and the correlation of the intrinsic ellipticities of both galaxies. So one, basically, because of causality, we can neglect it, but the fact that the background galaxy can be aligned with a structure that lenses it causes what's called an intrinsic GI contamination, and we also have this intrinsic if then the two galaxies are already correlated. And so this is a problem for this weak lensing analysis, because this causes a bias, causes a spurious signal in the analysis. And so in order to constrain this, we need to understand how galaxy properties are indeed correlated with each other and with the structures that then cause the gravitational lensing that we want to measure in order to infer the unbiased mass distribution in the universe. And so this is now very much sort of an ongoing industry of interest in order to calibrate models, develop models for this intrinsic alignment signals using simulations. And yeah, I do not have time to go into the details, but sort of the interesting result so far seems to be that the signal in the collisionless matter seems to be somewhat stronger than for galaxies that have sort of gone through a very inefficient galaxy formation process that sort of lost a lot of information about the formation conditions of the galaxies. Let me close with two more aspects, going back to cosmology, where we do care once again about sort of being able to describe the formation process of the cosmic web, which is sort of detached from the very, very nitty-gritty small scales of the galaxies, but is not the perfectly linear regime on which cosmologists like to stay. One aspect, for example, of precision cosmology is the use of the baryon acoustic oscillation feature, which acts as a standard ruler in the universe. Why? It is a scale that's imprinted in the perturbation spectrum by a process in the early universe, which we basically, we get an overdensity in the sort of an excess probability to find a galaxy at a fixed distance from another galaxy. And this comes about by a sort of acoustic wave that was traveling the early universe until recombination of the CMB. And this scale of about 120 megaparsec would be a perfect standard ruler if we could recover it perfectly. So the feature would look like something like this, but then because of each galaxy that sort of contributes to the signal is part of the cosmic web formation, the galaxies do not end up on a perfect circle, but end up sometimes in voids, sometimes in clusters, sometimes somewhere else. And so we have sort of a process that distorts this perfect standard ruler and washes out the signal. And so techniques are being developed to revert this effect and measure the signal in the best possible way. And in order to be able to do this, techniques like the Zeldovich approximation, or possibly even better techniques that we'll develop now and in the future, will help to achieve this reconstruction that is then consistent with the whole processing of the cosmological information. Let me close with the very, very last aspect is, can we use the cosmic web itself as a cosmological probe? This has been something that has been discussed also a lot in our community. Because typically the signal that we saw here, this comes simply from a two-point analysis of the galaxy distribution. A two-point analysis is fully justified for a Gaussian random field. So meaning we have sort of a Gaussian process which underlies all of structure formation. As we know, a Gaussian is fully described, fully determined by its mean and its variance. And so the two-point function is really just nothing else than the variance of a Gaussian. And so when we do two-point clustering analysis, it's very robust, but it only makes use of the variance. At the same time, we know that all the galaxies that we have, that we're observing, are not part of a purely Gaussian process. We have these very, very non-Gaussian features, these web-like structures. And so is there a better analysis than doing 2 points? Well, from sort of the theoretical side, you might say, well, then let's do 3 points, let's do 4 points. The problem with this is that's one way forward, but there might be sort of better ways that sort of contain more information from multiple points and at the same time are more robust in doing an endpoint analysis. And so this is something that's very much discussed. One thing that has been advocated as a very competitive road is what's called void size functions. So the idea is that one takes the galaxy distribution and then gets sort of a distribution of the sizes of the voids. And this is just an example from Session Adatur, where they find by including the voids information in the galaxy, baryon acoustic oscillation analysis, with Big Bang nucleosynthesis priors, they sort of reduce the error region in omega matter H0 by about a factor of 2. If they further include sort of Lyman alpha forest information with the voids, then this goes even further down. There is more sort of promising things in the direction. This is another example by Tony Bonaire from this year, where a standard 2-point analysis was carried out, but then sort of not taking any 2 galaxies, but sort of thresholding on galaxies that are in these different environments. So only calculating 2-point analysis of galaxies in filaments, galaxies in voids, and galaxies in clusters. And sort of by doing these conditioned 2-point functions, they found that typical constraints are improved by a factor of 8, which I think is sort of almost a bit better than what we see for the void size functions. There's also more sort of agnostic approaches that are being discussed in this direction. The key is sort of to go beyond the simple Gaussian 2-point picture in this context. So, for example, the wavelet scattering transform, which is an agnostic analysis, if you want, agnostic summary statistics of such fields, gives even better improvements than this 8 times on cosmological constraints. The problem is it's sort of less interpretable, that it calculates, gives you sort of some statistics that contain all the non-Gaussian information, but you don't know what exactly it is. You can sort of get it back out, but this is a little bit of a drawback of these approaches, while something like a void size function is a very intuitive concept. So these are things that are being discussed as well, extending the cosmological large-scale structure probes beyond 2-point functions. Of course, another example is galaxy clusters. Galaxy clusters as cosmological probes have been around for as long as cosmology is almost around. And that's why I didn't mention them here, but in some sense they are, of course, also part of this game. This brings me then to my summary and conclusions. So I hope I convinced you a little bit of the theory of, or at least gave you a little bit of a feeling of what goes into the theory of the formation of the cosmic web, the connected shocks and caustics that arise when these fluid elements cross, which causes mathematical problems for these perturbative approaches. Therefore, this is sort of the frontier of analytic techniques, perturbation theory approaches in this direction. With the simulations, we have no problem to probe this regime, but the simulation always only makes a statement about one realization of a universe and a set of cosmological parameters. So having sort of more flexible techniques is very important. I hope I also showed you how galaxies sort of form and evolve as part of a cosmic web. The connection, at least at low redshift, remains a bit unclear, but I think there will be very interesting things to be learned at higher redshift. I hope I also showed you a little bit how it, at one time, acts as a contaminant of precision cosmology by influencing galaxy formation, thereby making galaxies not perfect probes. For example, with these intrinsic alignments and small-scale nonlinearity. But at the same time, the cosmic web itself might be a very sensitive probe of cosmology beyond the simple 2-point or even n-point statistics. Thank you very much. I hope this was sort of at the right level for these presentations. Please don't hesitate to ask questions.
Thank you, Ollie. I very much enjoyed that. And thanks also for illustrating these concepts and what we've learned with such appealing view graphs as well. So yeah, I'm sure the frequent talk of pancakes has made some of the listeners who are approaching dinner time quite hungry, but we will take a couple of questions still. So just as a reminder, you can still write your questions in the chat, or you can also raise your hand, whereupon you'll be called on to speak up and pose your question directly. I think I'll start off directly myself today, sort of using my chair's privilege. Wondered, Ollie, if you could give us a feeling in very rough terms for what fraction of the galaxy populations or population as a whole lives in different environments. So how has this changed, say, nowadays, what fraction lives in nodes, in filaments, in voids, and how did that change from, say, 10 billion years ago or so in the somewhat earlier phases?
So this is a bit of a weak spot. So you I would say, of this analysis. For a Gaussian field, with a given any correlation structure, you can actually calculate. So if you define it like the way you would define it, you can calculate that then 8% of the mass or volume is in voids and clusters, and 42% roughly is in the other two. So now we know that the universe, of course, especially when these structures then have emerged later on, is no longer Gaussian. So these shift considerably, but the degree to which they shift depend a little bit on the exact definition of how you sort of tear these structures apart. And so in the end, you know, I could tell you some numbers, and but I have to confess I don't know them even on top of my head. But the problem is there's sort of, this will not be a precision probe ever to sort of say whether a given galaxy sort of lives in a pancake or in a filament. In some sense, it depends very much on how exactly you analyze these structures. I think there's sort of some agreement of the people who do this analysis to tune sort of the parameters so that everybody gets the answer of sort of what you expect it to be. And I think then what you find, I can pull up the numbers if you're interested offline. 1 second.
Yeah, well, yeah, we can take that offline in that case. But yeah, thanks. Obviously, yeah, I think we can all appreciate how difficult it is to also, in some sense, define where one structure starts and the other one ends. Right, as you've shown us, exactly. It's not very continuous, and that is one of the distinctly modern viewpoints in speaking about all this in general, right? That matter distributions increasingly with our more powerful instruments become essentially continuous, right? To a certain degree.
Exactly, yes.
So, yeah, good. Let me then go to the first question in the chat, which has come through from Stephen Spangler. So yeah, he refers to a statement you made early on saying that so far, there are no serious challenges to Lambda CDM yet. This cosmological model is preferred cosmological model of current times. So his question is, how much longer, in your opinion, can there be no laboratory detection of dark matter before there will be a problem? Which might also be a question we could ask of next week's speaker.
Yes. So I think this is a very good point. It depends a bit on the audience how I phrase statements like this also. So I think every time sort of I give the big picture, I think I find it extremely remarkable how well Lambda CDM sort of fits across the scales. Right? So indeed, there is the big big problem. We have neither a laboratory detection nor even a sort of a clear signal of an indirect detection for dark matter. All we have is sort of the act of it acting through gravity mostly, and we also have sort of more clear, I would say, other challenges which might be systematic, which might not. We have the H0 tension now. We have sort of a weaker tension with sigma 8. We have sort of coplanarity, possible coplanarity of Milky Way satellites. That's sort of hard to explain. So I think in the end there are, of course, challenges. Are they big? So I think that you can always, the problem is like with the gravitational waves, right? It might well be that dark matter takes another 80 years to discover. Who knows? Yeah, I don't know what the answer here should be. I think I keep, we don't have like completely destructive evidence, I would say, at all so far. It's sort of little cracks here and there that we don't know yet how serious they are. That sort of would be my take, I think.
Thank you, Ollie. So just tagging on to that, I mean, you indirectly showed one challenge which is currently of interest to the cosmological community, which is related to the value of H0, depending on the measurement method. And on one of your last slides, you saw this, you showed this figure from Nadatur et al. 2020.
Yes.
Where you seem to illustrate with this diagram that taking into account large-scale structure information can move you from one edge of the currently measured values to the other and potentially reconcile. Is that correct? And could you maybe comment on this a bit more?
So this last one here, I think it comes, I would have to check fully, but I think it comes almost exclusively from adding Redshift 2.3 Lyman alpha forest information. So which I think is interesting, to say the least. So indeed, yeah.
So, I mean, is the bottom line that this analysis of which you're showing us the plot here would suggest that current discrepancies could still be overcome because when taking into account all systematics? Is that the message of this?
No, I think the message of this is that there might be, I mean, that the most constraining here for finding the low value at the end is the sort of the Redshift 2.3 Lyman alpha forest, which is consistent with Planck, more or less, and not so much with the higher values. I think this will be my takeaway here. Okay. So. Yeah, I don't know. I don't know enough, I think, about the low redshift constraints to sort of say anything. You should invite those people. It's yeah. I mean, another problem with this is that sort of the explanations we have are, well, at least some of them are sort of not that appealing, like early dark energy. We already don't really know what the other two dark energies are that we have.
All right, so another question has come in on the chat. Oli, I believe you have this in front of you as well. So Alphonse Sterling writes a question regarding some of the equations, I guess you showed at the beginning.
Yes.
So yeah, I guess this relates to methodology. And the question is, in the initial description with the Boltzmann equation and the gravitational potential, what are the particles in the equations? Are they dark matter particles? Are they galaxies or something else entirely?
So this depends a little bit how you look at it. You could think of this, because we include all matter in this. We can also sort of distinguish between matters. There's any level of sophistication. So the way I like about it is it's just cold collisionless matter dominated by dark matter. So we take this simply as we only have dark matter in the universe, and the rest of the matter would have sort of a collision term here, but it's only 20%. So as long as we stay on large scales, we do not have to worry about this. If we then add the sort of the baryons as well, then, and we want to describe sort of the true phenomenology sort of at the astrophysics level, then we have to add fluid mechanics, we have to add sort of all these galaxy formation processes of stars and so on that people are doing in cosmological simulations. At the same time, we can also think of this simply as sort of a hypothetical cold fluid, which describes everything, including galaxies on the large scales. It just means we're simply neglecting individual particle collisions, and we assume it's reasonable to sort of approximate in the continuum approximation. That's all.
Okay, and then the second part of Alphonse's query was then, in some sense, a very fundamental one, and maybe one which is useful to address, especially for people who are not working on galaxy formation. So when do galaxies form, before or after the web forms from the dark matter? And in some sense, I guess one could also extend this a bit to ask, in the early universe, in which topology or feature in the dark matter web are galaxies most frequently forming?
So I think we always assume that the dark matter is always colder than the gas at any time, right? Unless we have sort of special dark matter models. And so then the idea is really that sort of the dark matter structure forms way before any baryonic structures form, at least in CDM. And then at some point we'll have a halo, in which the first stars can form in this picture, right? Where all of a sudden sort of cooling, we're exceeding the Jeans mass, cooling starts being efficient, and so on. We're forming the first stars, we're forming the first galaxies. So in CDM, there is this picture. Now, if we go away from CDM, then you could have cases where we sort of have genuine baryonic structures. Like we could think of galaxies also forming in filaments that have no sort of associated dark matter clump. So they're really sort of, there's first the baryonic galaxy forming, and it pulls in the dark matter later on. But I would say this is not in the standard sort of CDM scenario that it would go this way. So in CDM, it's always dark matter forms first, then there is always the halo, and there forms sort of the potential well, and then which then the galaxy forms. And as the stuff merging in or flowing in along sort of the filaments into these structures, there will be then also accretion of gas and so on.
Okay, so I guess what looks like it'll be the final question potentially comes from Niels Wittenburg, who raised his hand. I see, Niels, that Willy has enabled you to speak, so you can ask your question now.
Yeah, thank you. First of all, thank you for the talk. Hope you can hear me.
Yeah.
I'm also doing some galaxy formation calculations and recently also cosmological simulations. And I was wondering, as I'm doing this in a more non-standard cosmology, I was wondering how fast do these, the web itself, does the web itself form? As you just told, it's especially in the very standard picture with CDM, the CDM precedes the baryons, right? So you get the structure first. Do you have a measured or distinct redshift where you would expect the CDM pattern to form, and when the baryons form or should form? It's more like connected to the JWST results, right? Like how fast can this actually be?
Yeah, so I think you should ask again the people doing the high redshift formation. So I think what you typically find is the first structure somewhere. I mean, the first galaxies, what is it, redshift 10-ish or so? So I think these redshift 15 are indeed a problem. Then you have to work out the exact numbers. It drops very, very quickly. There are other things you can do to make it accelerate outside of lambda CDM, of course. So I think this is, if they really turn out to be redshift 16 galaxies, then yes, we have to do something. But I think so far it's not so clear that they are really there. So we'll have to see spectroscopic confirmations. There are even some arguments that they sort of the masses would be possibly in contradiction to how many baryons they're even available, and things like this. So we'll see. The cosmic web forming. So I think at these early times is actually particularly simple in CDM because we're sort of in the power law phase of the perturbation spectrum, and so it's almost close to self-similar, meaning the web at any given time is the same as at a later time on just larger scales during this phase. And only now that we're sort of the nonlinear scale is close to where we have the peak in the power spectrum of matter fluctuations. This is somewhat broken, this self-similarity, but in these early phases, I think it's pretty much that you can just scale it up, scale versus time.
Okay, nice, thank you.
All right, and I guess the interesting bit is also, right, once you find these early galaxies and can measure certain properties for them, you can already have some ideas of how much earlier they must have started putting their first building blocks in place as well. So you can even backtrack a bit more beyond just noticing that they are already there. So yeah, JWST clearly will tell us a lot, as will H1 tomography experiments of the early universe as well.
Absolutely, yes.
Good. Well, Olli, that brings us to the end, essentially. At this point, apart from thanking you again for being with us today, always look ahead to the following week. So next week we will be back here again at the usual time. So 1500 Universal Time or 1700 Central European Standard Time, with a talk, as was also already mentioned today, on dark matter, and now really about the properties of dark matter and astrophysical searches for evidence of dark matter. So our speaker next week will be Tracy Slatier from MIT, and we're looking forward to that. Remains for me is to thank Oli again for being here, and the rest of you for joining. And yeah, have a good rest of the day or a good rest of the evening, and see you soon again. Bye-bye.